So we will begin from last class, right. So last class we are looking at laser arc laser welding, and then the last unit, so we also looked at laser arc hybrid welding. So how to combine both arc heat source and the laser, so that we get the maximum benefit out of the both heat sources, right. So laser welding, it has its own limitations because of the faster cooling rates and the very narrow fusion zone. Okay, so the mechanical properties of the welds may not be as good as sometimes in the arc welding process. Moreover, in the arc welding processes, so you may not have a good penetration. So by using both the laser heat source and the arc heat source, so we can get the benefit of the both processes, right. So we can get a deeper penetration, and we can also increase the width of the fusion zone, and so that we will have a good fit up. Okay, so we can also slightly increase the bead geometry in such a way that you may not have a strong load partition into the fusion zone. And by using arc we can also fill more volume, isn't it? Because GMAW, if you use filler, it also gives more liquid metal which can be used to fill the cavities, right. Otherwise you will have to melt the interface more volume of materials. So in GMAW you can use a filler to fill the well cavities, and then laser can be used to achieve a deeper much deeper penetration. And then we looked at the electron beam welding, the first slide we looked at. So electron beam welding is also another type of power beam processes, right. But in the electron beam welding compared to laser, the power density of electron beam is much higher, right. So we can make use of the high power to make very precise narrow bead weld for various applications in the electron beam welding, right. So we can achieve extremely narrow weld zone using electron beam welding, because in contrary to laser absorption of the material is very low. Like, so as I said, an aluminum does not absorb any laser lights, and steel maximum 30%, that is what is going to absorb, whereas the absorption of electron to material especially in alloys are much higher. So the efficiency of the process is quite high. That means that 90-95% efficiency we can achieve by electron beam welding. So that means that if you have a power of 2 kilowatt of electron beam, okay, which is passing to a workpiece, and almost 90-95% of the power which is actually there in electron beam can be absorbed by the material, because the absorption of material by electrons, it is much higher, okay, than laser. So the efficiency of the laser electron beam welding is very high compared to laser, and we can make use of the power which we generate for laser to melt much more volume, right, and much more thicknesses to generate deep penetration welds using electron beam welding. So that is why the electron beam welding is widely used for various strategic applications. Okay, so why they are used? Because we can achieve a good fit up. That means that the weld can be made with very narrow regions, and because of the very narrow heat source we apply, the temperature gradient is also extremely steep. Okay, so if you look at the electron beam welding, the temperature distribution, so this is the weld center line as a distance. In electron beam welding it will be extremely narrow, right, whereas in GMAW, so you will have a much wider fusion zone, and then, right, so this is so distance and the temperature. On the laser beam welding, so it will be slightly higher, the temperature gradient will be slightly lower than the electron beam welding, so something like this, right. So this is the arc, the laser, and then this is EBW. Okay, so in the electron beam welding, the temperature gradient much steeper than laser, much steeper than the arc welding, right. So suppose if you have a weld made, say suppose this is your interface, in laser beam welding, so suppose if you are achieving a weld bead geometry something like this for this thermal profile, in electron beam welding it will be much narrow, right. And for arc welding, so it will be much shallow and then wider, right, it is clear. So, because of the temperature gradient and then the focused heat source what we use, and your depth of penetration approximately much deeper in the laser and electron beam we may achieve a depth of penetration, but the weld zone width will be much lower in electron beam welding because of the very highly concentrated the heat source what we use, right, it is clear. So, now so what is source of electron? So, the electron generation we already studied about in the first chapter, right, thermionic emission and the field emission, right. So, using a low current and extremely very high voltage source we can achieve field emission as well as thermionic emission, right. So, breakdown voltage, so you remember, right. So, we will have to achieve very high voltage and to say generally 4 kilovolts and very low current, some 100 to 200 milliamperes current is supplied to an electron source which is the target, which is also the cathode, right. And then we can apply a very high breakdown voltage to emit the electrons from the source, and that can be accelerated towards the anode which is the base material, right. So, you can keep the acceleration voltage. Based on the acceleration voltage you may also gain the energy, the power in the beam, and unfortunately when you are accelerating the electron that are generated from the cathode to anode, the electrons would also diverge. It is not like laser, is not it. So, now we need to use some lenses which can also converge the lens, converge the beam, and then can be focused onto the workpiece using electrostatic lenses or magnetic lenses, because the electrons can be focused, defocused, converged and diverged using magnetic and electrostatic lenses, right. So, the electron the optics gun is similar to any other electron microscopes you can imagine. Only thing is here the beam energy is much higher than what you use in electron microscopes, right. So, what you see over here is a simple schematic of an electron beam welding setup. So, this is the cathode assembly, is not it, and you apply in a very high the voltage to emit the electrons, and this is for much higher electron power 160 kV kilovolts. So, you can generate about 30 kilowatts of power using electron beam, okay, it is much higher. So, entire setups would be in a very high vacuum, and then we can use the electrostatic and magnetic lenses to converge the beam as well as to focus the beam onto the workpiece. And so, we always know that cathodes would be negative and then the anode can be positive, and we can maintain the voltage differences between the cathode and anode, and that will determine the acceleration voltage and then the power, the acceleration power what you achieve from the electron beam, and it can be accelerated based on the voltages that are kept between anode and cathode. And then using the lenses we can focus and defocus the beam onto the workpiece, and then the spot size is much smaller. We can achieve much smaller spot size than even laser, but we can focus and very high power onto a very tiny spot. Actually, due to that now we can have a very narrow heat affected zone as well as the fusion zone, and the material absorption of electrons also much higher. So, electrons would penetrate the material much deeper than the lasers, right. So, moment the electrons are deaccelerated, so obviously, so the kinetic energy of the beam is dissipated as a heat in the material, and then you end up melting the interfaces, forming weld, right, it is clear. So, I do not want to get into how the lenses work, electrostatic lenses work, and these are all simple physics, right. So, you do not need to go about the optics, what we concentrate on the welding by using electron beam. So, we assume that we have the electron beam setup. So, what are the parameters we can control, so that we can control the beam pressure, and so what are the geometrical designs we can achieve using electron beam welding. That is what we are going to see, right. It is clear. Any questions? We will move on. Okay. So, the keyhole again formation is the same as laser beam welding, right. So, what are the 3 forces that aid keyhole formation? The beam pressure, vapor pressure, and then recoil pressure. In electron beam welding process, the beam pressure is much higher than laser beam welding. So, in a way it is difficult for anyone to do a welding in conduction mode using electron beam. Okay. So, in all the cases when you use electron beam, you always use keyhole welding in electron beam welding. So, why? Because so if you look at the beam pressure, the pressure which aid the keyhole formation, okay, the main pressure which actually aids is the vapor pressure and the beam pressure. And if you look at the beam pressure, so for laser beam welding, the beam pressure is the power divided by the cross section area and the velocity of light. Okay, so the what you have it is from your the laser power source. Okay, so in electron beam welding, the beam pressure is controlled by the current density, which is the electrons we generate in the source, and then V, which is the accelerating voltage, the voltage between your target, the base material and the electron target, the cathode. Okay. So, you can also increase the beam pressure by changing the acceleration voltage, and you also have the current density. What is current density? Is the number of electrons, right, number density that is generated from the cathode. Okay. So, that can be changed by changing the voltage in the cathode, the target, the breakdown voltage. Okay. So, that can increase the number density of electrons that are generated, plus how fast those electrons that are generated accelerated from the cathode to anode, and both would contribute to the beam energy, right, beam pressure, right. So, the M and E, these are all electron mass and the charge, right. So, the J and V determine the beam pressure, and if you look at the beam pressure of electron beam welding, it will be much higher, right. The beam pressure in electron beam welding, it will be close to, if you do a simple mathematics using a target current of 100 milliamperes, and then the acceleration voltage of 100 kV, and we can achieve the beam pressure of 300 Newton per meter square. So, 300 megapascal. Okay. So, that is huge, the beam pressure itself. Okay. So, it is acting. Now, imagine this is newtons per square meter, and the beam size is few microns. Okay. So, the pressure which is acting on a very tiny area is huge. So, even if you have an acceleration voltage of 100 kV and then a beam current of 100 milliamperes, the amount of energy which is actually sent, the pressure is there by the beam at the keyhole is huge. So, you always end up making keyhole. Now, keyhole cannot be closed, because compared to the beam pressure, the surface tension and the gravity is negligible. Okay. So, surface tension is the formation pressure, I think it is -3, I will check it and then correct. The surface tension is much lower, gravity is much lower compared to the beam pressure, the vapor pressure and the recoil pressure. Okay. So, the surface tension and then gravity which are actually closing the keyhole is negligible compared to the pressure we have in the beam, the vapor pressure and the recoil pressure. So, recoil pressure you see that it is 10⁻⁷ Newton per meter square. Okay. So, huge, because of the vapor that is actually pushed from the weld metal to the atmosphere. So, whatever mode you actually use, whatever current, acceleration voltage, in most of the cases you will end up making keyhole in laser beam welding, in electron beam welding. Whereas in laser beam welding, so you can make a weld without keyhole in a conduction mode, that is possible, but in electron beam welding, whenever you weld, you always see that the keyhole shape. Okay. So, the keyhole shape would always be like this. So, what you see over here, So, this is 15 centimeter, it is not millimeter. Okay. So, that is 150 millimeter, and you see you can achieve a full penetration of 15 centimeter, and you could have a full penetration of 150 millimeter. So, 150 millimeter, 15 centimeter, something like this of steel, okay. And you can have a complete penetration in a single pass. Yeah.
Sir, in case of laser beam welding,
Yeah.
Yesterday we discussed that sometimes the beam pressure is so high it might lead to that hole, like from here it will pass and it will pass
Yeah.
to the other end.
Yeah.
So
Yeah, this is also a hole.
this
Yeah.
problem will
Is
arise.
always be there. That is a problem in electron beam welding. The beam pressure is so high, you always have a through hole, right? And then this hole has to be closed. And if you look at electron beam welded joint, always at the top position you always see a hole. Okay, so that is why we need to have a proper start and stop control, so that the keyhole at the end can be filled by the surface tension of the molten pool. So, we will have to make sure that at the end of the at the end stage or the last stage of the welding, and you will have to reduce the current or the power in such a way that you do not form a full keyhole, you just melt or superheat the liquid in such a way that the liquid can fill the keyhole which is formed by the high power beam. So, if you do not do that, if you do not use a proper stop procedure, the keyhole would remain as a keyhole, because the keyhole would not be filled by the surface tension of the liquid. Okay, so that is why when welding is done at the end, electron beam welding, we always maintain a very low current or low power in such a way that we just melt and then or superheat the liquid which is there and surrounding the keyhole at the end of the weld. Otherwise, if you look at it, even in laser welding, if you are not doing if you are using very high power laser, and if you are not doing proper welding procedure, at the end there is a pinhole, the keyhole remains at the end of the weld, right. So, in this case, so this is actually done in a flat slab. So, if you are doing it in pipelines, so you will have to make sure that at the stop, I mean you need to either defocus the beam, or in the laser you also have to defocus or maintain a low power in such a way that the molten metal is heated and you are not forming any keyhole, and you are doing in conduction mode, and then the liquid which is there can fill the hole. Otherwise, you will see a pinhole at the end of the weld. Okay. So, now imagine the power of electron beam. So, this is a 15 centimeter slab, and you can achieve a single pass weld, whereas in this is in GMAW. For 15 centimeter, 1 centimeter, you need to have hundreds of passes. So, you see this is one pass, right. So, imagine how many passes you will have to do in this cross section, right. So, it will take enormous amount of time and energy and then manpower to achieve a weld of such a thickness. So, that is why the electron beam welding is very widely used for such an application. Okay. And so, what are the advantages of electron beam welding over laser beam or any other welding process? And electron beam welding, we always use it in autogenous mode. What is autogenous mode? No filler. Okay. So, nowadays we also developed 3D printing, additive manufacturing using electron beam. Okay. So, Siaki is a very famous company, or EBAM. So, they make the equipment using electron beam for additive manufacturing, and where we also add filler to deposit layer by layer to make components. But for welding, electron beam welding is always used in autogenous mode. Okay. And because of very narrow heat affected, I mean the power source, the surface preparation should be extremely good, and the fit up has to be perfect. Even a small roughness and small distortion is not going to make a good weld. Yeah. So, other properties of the electron, we will have to make it, we will have to make sure that the electrons are generated and then transported in vacuum, otherwise it is going to ionize. Now, we are going to lose all the electron properties, the energy. So, generally so I think it is 1. the electron beam requires a typical vacuum 10 power minus 3, 10 power I think minus the low electron beam low vacuum system can also be used. Okay, so the low vacuum it can go up to 10 power minus 1 as well. Okay, we will go back to that, and it has a very high process efficiency, 90%, because of the very high absorption, because optical spectrum laser the material does not absorb effectively, but electrons can bombard the material, right. So, laser efficiency much lower, say not even 10% for aluminum, whereas 90% can be achieved in electron beam welding. Okay. So, one of the disadvantages of electron beam welding is electron beam is extremely expensive, the setup. So, the problem is the very narrow weld zone. Okay. So, because obviously the power source is very narrow, and the electron beam welding advantage is the very reactive material can be welded because the welding time is much lower, and for example Ta64 titanium it oxidizes very quickly, and laser beam welding and JMIW welding if you are using, you need to have a proper shielding, or you need to do it in a glove box. The welding has to be done in a controlled atmosphere, so otherwise it is going to oxidize and it is going to get only powder. And because of a very narrow weld zone, the cooling rates can be very high. Okay. Cooling rates can go up to 10,000 Kelvin per second, even higher. So, that is why when you have a material which has a history of phase transformation, especially low carbon steel for example, and you will end up getting a very fine martenseric microstructure. Okay. So, and that may lead to cracking. Good. So, this we have seen. So, this is the basic the sequence of weld formation. So, first we need to make sure that the edges are prepared nicely. There should not be any mismatch. The both should be coplanar, absolutely perfect. Dimension tolerance is less than a micron what you achieve. Otherwise, suppose if this is somewhere up, something like this, it is not going to work out. Okay. So, because if it is not fit up properly, if they are not if they are misaligned, then you are not going to make a joint. Similarly, the surface preparation roughness. So, if it is not done properly, and it is also not going to work out, right. So, the moment you have a beam, you have a melting happens, and once the melting happens, obviously the beam pressure and the vapor pressure would start forming a keyhole, right. So, the keyhole would form because the moment you melt, you will start vaporizing, is not it. So, the vapor pressure, the beam pressure and the recoil pressure would start developing a keyhole by pushing the liquid surface away. Okay. So, the keyhole is formed here because of the beam pressure which is acting this direction, and the vapor pressure and the recoil pressure, right. So, then you will have a keyhole formation at the edge, and then you keep on focusing the beam. So, obviously the keyhole wall will be extended and you will have a full penetration keyhole, and the molten volume would encompass the keyhole, because the surface tension would never close the keyhole, because the keyhole formation forces like beam pressure, vapor pressure, recoil pressure is so high, your keyhole will never be closed. Okay. So, and then the moment the beam is off, obviously you will have solidification, and then the surface tension would make the liquid interface to coalesce, and ultimately it will solidify. Yes, it is clear. So, the sequence of the weld formation. Any questions? Okay. So, in most of the cases we need to maintain a very high vacuum. So, nowadays we also have an atmosphere system. So, but it is not really atmosphere system. You still have electron gun, but the sample can be in atmosphere. So, in all cases the electron gun should be at very high vacuum, okay. But you can make sure you can develop a system in such a way that the sample can be outside and very high vacuum system, right. So, that and you can achieve a good keyhole stability. and you can also manipulate the sample. Okay, so suppose if you are doing it in a very large volume of material and you can't keep it inside the vacuum chamber. Say for example, weld I showed you 150 centimeter slab, and if you want to keep it inside the vacuum chamber, and you need to have a big huge setup. And in fact, there are setups which you can do in a meter component as well, but then the investment cost will be very high. Okay. So in that applications, if you have a non-vacuum or low vacuum system where the sample can be kept at a reasonable room atmosphere and slightly lower vacuum, then be very beneficial. Yes, it's good. Nice. So the most preferred joint design is the square groove butt joint. Okay, and all the configuration, if you look at it, it is the manipulation of the butt joint only. Okay, so you can have a slightly inclined butt joints, but in most of the cases is always a butt joint, and varying configuration you can achieve. And you see over here melt through weld, and this is can be achieved only by electron beam. Okay, so it is like you join two, and you are not doing fillet weld. So fillet weld you do on a melt through weld. So you can, because the electron power is so high and you can achieve deeper penetration. So the beam can be penetrated and then molten, and you make a joint between two interfaces, the melt through weld. And this is better than you having in a fillet weld, because in a fillet weld you add extra material, and you also have a stress concentration points, isn't it? So when you are using a fillet weld at the joint, so you also have a stress concentration, and then you also add extra material to make a fillet joint in T configuration. So in that application you can use an melt through weld. So you can have an electron beam passed, and then you can make a joint between these two surfaces. It's clear? Some of the configuration, if you look at it, most of them are butt welds. And some other configuration. So yeah, the T joint and L joint, and it is very well done in electron beam welding using a melt through configuration, whereas in other joints, so you will have to do a single groove or double groove T joints. On electron beam you can achieve a simple melt through welds. So if you want to use GMAW, so you will have to use a single fillet welds or double fillet welds to achieve similar weld configuration. Yes, it's clear? Any questions? So this table shows the energy input we use and what depth of penetration we achieve for a given composition of the material. So for example, in copper, the energy what we need kilojoules per millimeter. Okay, so in iron, and this is a reference table which you can use it.